So this session is particle motion in the plane. It's a calculus session, and our presenters today are Mr. Tom Dick. He is from the West Coast, Oregon State University. I believe those are the Beavers. Is that correct, Tom?
Good job.
Is okay. He's also one of our national instructors, and he is a former chair of AP Calculus Development Committee. He will also provide a little more background when I also pass over the control to them. The other presenter is Steve Kakashka. He is also one of our instructors. He's from the East Coast. He's from Bloomsburg University, and he is also involved with AP Calculus reading, and he's a member of the development committee as well. He'll provide you guys also with more background information once I pass over control to them. Bottom line, both of these two gentlemen are much like 10 times smarter than I am. They will be providing you guys with a lot of good resource and knowledge throughout this session. But one thing that we will be doing, and one thing that we've been asked to do is to select also a winner of some technology. So before the end of the session, we will be selecting someone that that will win some technology, and I'm going to ask for their contact information through the chat. So make sure you are able to use the chat feature to provide that for us. But here's the agenda of what we're going to cover today. We're going to go over some background and definitions. I believe Steve is going to talk about how to use technology and how to solve some of this, analytical questions. And then the link that I've been sharing in the chat is for a homework problem that I believe Steve wants to entertain with you guys. And then some discussion on some scoring, AP Calculus exam scoring that both Steve and Tom are going to talk to you guys about. At this point, I'm going to stop sharing. And I am going to provide controls over to Steve.
All righty, how about that? Can you see that, Marco?
Yep.
How's that? Beautiful. Well, thank you very much for that introduction. I'm delighted to be working with Tom again. Just a couple of little things. Tom and I do a regular webinar series for Texas Instruments called Monday Night Calculus, and we do address specific topics during each session. But if any of you have a specific question that you would like us to address during that session, please feel free to send it to one of us, or you can send it to our moderator Curtis Brown. We'd be delighted to look at that. And those sessions are not only for teachers, but also for students. It's wonderful to have them involved. Well, Tom and I have done a lot of presentations together, but we rarely have the opportunity to do a BC topic. So this is kind of fun for both of us. We're going to be looking again at particle motion in the plane. And we're going to be solving some typical AP calculus type questions. I'm going to solve at least one or maybe two of these, one analytically and with technology. Tom's going to introduce a little bit more with technology. And my technology screenshots are generally with the TI-Nspire, and I often graph a lot of things with Mathematica. Tom will show you a little bit more with the TI-84. So bear with me. I just want to remind you of a couple of definitions and formulas, and then we'll start to solve these problems. And by the way, I believe the link that Marco gave you in the chat is actually a link to a complete handout with all of the problems, examples that we're going to discuss, so that if you have that link and are able to, by some fluke, print that out, you can write right in there and follow along with us. All right, so the first thing is I want to remind you about functions. You know, if you had the opportunity to listen in to participate in the AP pre-calculus session earlier today, they were stressing how important the notion, the idea, the definition of a function is, and used in many different ways. And I still remember my calculus teacher in college telling me that this was the most important idea concept in all of mathematics, and indeed, I still believe that. And I know Tom wants to ask me, well, what's the second most important idea? And I've always believed that it's absolute value, that if you know those two things, the definition of a function, the definition of absolute value, you're off to a good start. So today we're going to talk about some special kinds of functions called vector value functions, and I won't read through all of this with you. This, in fact, is on the handout and will be available in the additional handout that we provide to Marco. This is a function whose domain is a set of real numbers and whose range is a set of vectors. So we're going to be looking at vector valued functions today. And these vector valued functions have components, let's say f of t and g of t. They're called the component functions of a vector valued function R. And we often use this notation. And being involved with AP Calculus, Tom and I get questions about notation frequently, and one of them is about this sort of notation, using this sort of what I might call angled brackets to represent a vector. And, you know, do my students have to use that kind of notation? Well, not necessarily. It depends upon the context. It depends upon the question. This is probably pretty typical notation for a vector, and we really like students to use that. But depending upon the context and how a student responds to a question, we're very sensitive to different kinds of notation. So there is this connection between vector functions and particle motion. Those of you teaching BC calculus are aware of this. If we have a particle that moves in the plane, so that out of time t, the position of the particle is given by those values, x and y, x equal f of t and y equal g of t, then we can consider this vector function. And r of t is the position vector of that point, f of t, g of t. And therefore, any continuous vector function describes the position of a particle in two dimensions. I'm just going to circle this for a minute. Some of you are lucky enough to teach multivariable calculus in high school. And thinking about vector valued functions in 3 dimensions is really cool. There's some beautiful pictures and graphs that you can get in 3 dimensions, and that's for another time. I wanted to remind you of one more thing here before we get to a couple of formulas. How do you take the derivative of a vector valued function? Well, it turns out that you take the derivative piecewise, or term by term, or component wise is a way to think about it. So that r prime is simply f prime, the vector f prime of t, g prime of t. Fantastic. Couple more little things. So suppose we have a particle that moves along a curve C, and its position vector is given by this function r of t. The velocity vector is given by that derivative component-wise, dx dt, dy dt. I want to remind you that that velocity vector has both direction and magnitude. So the speed of a particle at time t is simply the magnitude of that velocity vector. Think back to maybe some of your linear algebra classes. Think about what you learned about vectors. And the magnitude is simply the square root of dx dt squared, dy dt squared. The total distance traveled by a particle from time t equal alpha to beta is given by this definite integral. And finally, down at the bottom, the acceleration vector is given by d squared x over dt squared, d squared y over dt squared. I'm going to go out on a limb here and say for those BC calculus students who are preparing for the exam in May, if indeed there is a particle motion in the plane problem, on the free response portion of the exam, many of the questions will revolve around these ideas, these concepts right here. And so that if your students are able to know these concepts, are able to apply them either analytically or most likely using technology, they can secure most of the points on that free response question. All right, so I'm going to try one here. I'm going to scribble a little bit. Remember that this was in the chat, and so you could follow along with this one. I'm going to show you a little analytical solution once in a while. I'm going to show you some technology solutions, and then eventually I'll hand it over to Tom. So here we have a particle moving along a curve in the xy plane. Its position is given by x of t, y of t, given there. Generally, these problems on the AP Calc exam, generally these problems are on the calculator active portion of the exam. And these values, pardon me, these functions x and y that are given, or sometimes dx, dt, dy, dt are given, are complicated enough that you can't easily integrate, okay? So the first part of this is to simply sketch the path of the particle and use some arrows to indicate the direction. Well, look, this is clearly done much easier, much more efficiently with technology, but I'm going to add in a little bit here. I'm going to try to anyway, add in a little bit here that I think I can get analytically. Let's see if I can do this. I believe that this particle starts over here at the point -1, 0. So I set up here that this is true for t greater than or equal to 0. So let's just see for a minute if I can take a look at x of 0. And don't let me make a mistake in this one. This would be the log of, let's see, 1 minus e to the 0, which would be 1, plus 2 times 0, which would be 0. Log of 1 is 0, and so that's -1. And I think because of the nature of this function y of t, you can see that y of 0 would be 0 times the cosine of 0. So that's going to be 0. So indeed, this particle starts at the point in the plane -1, 0. It's going to be moving off here to the right, and be careful. It kind of looks like it crosses the x-axis at 1, but I don't think that's correct. But I do believe it crosses the x-axis when t is equal to 1, and I think you can see that by looking up here at this expression for y and evaluating that at t equal 1. And then if we take a look at x equal 1, we would find that position on the x-axis where it crosses. Gee, there's lots of cool questions that I have here. One question I might ask about this is, which I didn't in this example, is can you find the time when this curve crosses itself? That's kind of a cool one. It looks to me like this curve moves in this direction. It crosses the x-axis again over here. I'm going to add in a little bit more for later. Could you find the value of t where that occurs? It circles back around, crosses over the x-axis again, and goes down this way. And here's another question, and I'll just put a question mark out here. Where does the motion of this particle go after that as t increases without bound? And in order to answer that question, you might take a look at, again, the nature of this function y. It's got a periodic function in there, cosine, so that's kind of a hint. And what happens to this function as t increases without bound? So you might think about some of those, and down towards the bottom, I've got some screenshots from my TI-Nspire, which I think is pretty cool. One of the reasons that I really enjoy using this calculator is because it gives me answers symbolically, the exact symbolic answer. And so what I did is I started out by defining f and g. So I placed those in, used that on a calculator screen to find f and g on a calculator screen. And then over here on a graph screen, it's easy to graph parametrically. And so I can see the motion of that particle in the plane. It looks like my picture up above, which I generated with Mathematica. And I can actually use, I believe, a trace feature on the calculator to look at the motion of that particle and to add those arrows into my graph. That's pretty cool. All right, part B. Let's see if we can find the velocity vector and the acceleration vector at time t equal 1. Holy Toledo, there's a lot on this page. So as I try to solve some of this, I'm going to do that thinking about the AP Calculus exam, so bear with me about how some of this might be scored if it's on a calculator active portion of the exam. Let's think a little bit about that together. So the first thing I've got to do to find the velocity vector is I have to find x prime of t and y prime of t. So here's x prime of t. If you happen to have x of t and y of t in front of you, if you've been able to download that handout, remember that x of t had a log function in it and an exponential function and a 2t, a simple polynomial in there. So what I had to do there was take the derivative term by term. So now I want to know, well, what's the derivative of x at 1? I plugged all of that in. And a little bit of simplification gave me that value. So I'm finding my velocity vector symbolically, exactly. Let's see, in order to find y prime of t, if you remember, that was t times the cosine of an expression. So I actually have to use the product rule. I did all of that and a little bit of simplification out here. I evaluated y prime at 1, and that reduces nicely to a minus pi over 2. So here's the velocity vector, 3 minus the square root of e over 2 and minus pi over 2. That's kind of cool. One thing I did not do, which I probably should have, and something that you should think about, is actually finding the point, x of 1, y of 1, finding that point on the curve, and then graphing the velocity vector at that point, and of course graphing the acceleration vector. All right, to find the acceleration vector, let's see, I've got to find the second derivative. All right, so I'm looking up here. Where is that? Cheapers, I got to use the quotient rule there, take the derivative of an exponential. I did so. I evaluated. Hey, it simplifies pretty nicely. Minus the square root of e over 4. Same thing with y double prime. Let's see, what happened there? There's y prime. Well, I can take the derivative of that pretty easily. Got to use the quotient rule there. And lots of constants, pi over 2 hanging around. There's my expression, and that simplifies nicely. So that there's my acceleration vector. And look how easy this is with a TI-Nspire. So when we create the exams, great care is given to make sure that someone with a CAS calculator does not have an unfair advantage over someone who is just using one that does things, solves things, finds values numerically. So I took the derivative over here of f, the derivative of g. So there are my components of the velocity function, and it's fairly easy to find the second derivative. There are the components of my acceleration vector, and that's pretty cool. Good.
Steve, someone is asking if you are going to be posting or sharing this file.
Absolutely. I'll be sending it to you, Marco. Absolutely.
Perfect, perfect. They were wondering if they needed to be taking really fast notes.
Absolutely, we'll be posting it.
Perfect, thank you.
So find the speed of the particle at time t equal 4, remembering back to my formula there, the square root of x prime of 4 squared plus y prime of 4 squared. So remember, I found x prime a minute ago on that previous page, so I plugged in a 4, got that expression, plugged in a 4 for y prime. I think this actually simplifies pretty nicely because that's 0, and I think that's just a 1. And so let's see, I think if you square that out and do a little simplifying, you get this. There's my 1. And numerically, I think it's a 1.581. So that's pretty nice. And here it is on my CAS machine. I apologize for this. It's kind of hard to see, but up at the very top here, there is a square root up there. And so I took the square root of the derivative of f, evaluated at 4, squared it. Derivative of g at 4, squared it. And this is really cool. Notice that the Nspire comes back and gives me an exact symbolic answer. Doesn't look exactly like what I have up here, but I think if you stare at that long enough, you can sort of see what happened. The TI-Nspire squared everything out, collected some terms. There it is right there. And I did this trick. I like this one. I multiplied by 1 as a decimal, in order to convert that expression to a decimal, which is 1.581. While we're here, we'll just remind people of the 3-digit rule in AP calculus. So wherever a decimal answer is expected, it must be presented with 3 digits to the right of the decimal, rounded or truncated. And you probably already know that I like to present answers rounded, but we'll accept either. If a student presents more than 3 digits to the right of the decimal, then in grading or scoring that problem, we just ignore everything beyond the 3rd digit. And I do want to remind people that if there is an intermediate result, you should always store that intermediate result in your calculator to the greatest degree of accuracy allowed. So don't read that off your calculator screen and say, oh, well, just take the first 3 digits, store it somewhere, and use it in further calculations. I think I've got one more question here, Tom. I'm sorry about that. Let's see if we can find an equation of the tangent line to the path of the particle at time t equal 2. Well, I need a point on the curve. So there it is. There's x of 2, y of 2. To find the slope of the tangent line, y prime of 2 over x prime of 2. I've already got y prime. I've already got x prime. Plugged it in, did a little bit of simplifying. There's the symbolic equation, whoops, of the tangent line, and I got some decimal approximation. And Tom knows I always like to back things up here with a picture. So here it is down towards the bottom of my screen. There again, overlaid is the path of the particle. There's the point, and there's the tangent line, and you know, it looks pretty reasonable. Pretty cool. Tom, I'm going to let you do a little bit of technology, and then I'll come back and do whatever else I can. How about that?
Sounds good, Steve.
Okay. There you go.
Okay. Try to share here, and I'm going to pull up, I hope, TI-84.
Got it.
So I'll be using a bit of both platforms. One thing I'd make real clear, so Steve illustrated the use of the TI-Nspire with a CAS, computer algebra system, but there's tons you can do with the TI-84 or the TI-Nspire non-CAS, and that's why I wanted to start out with this. And in fact, either of those calculators is going to serve you fantastically well on the AP exam. You're going to be able to do things very easily. So on the TI-84, for example, one thing we'll need to do is most of the time you're going to probably have your calculator in a function mode. So your y equals menu will have y1, y2, and so forth. To change over to parametric mode, you'd find that, and you can see that I've got it there already down there on the 5th line. I'll go ahead and change this back. If I enter function and go to y equals, that's my usual y equals menu. If I go to mode and scroll down to that line again, go over to parametric. Oops, let's see. There we go, enter that. And if you go to the y equals, then it's going to be set up optimally for this particle motion in the plane. I've taken liberty, you can see it, I've got function slots here that are in pairs. So I've got an x1t, y1t, and I've taken the liberty of going ahead and entering in to those two components the functions that Steve was just looking at. Okay, so there's our x1t, y1 of t. If we look at the window, the setup's going to be a bit different. We're going to have a Tmin and Tmax. We're using T as the variable. And notice there's this another thing, the T step. So that's going to set the increment that T will advance by. It's kind of default settings. I think for Tmin, Tmax would be like 0 to this decimal equivalent of 2 pi or approximation there. But you can set those to whatever you want. And then the window here, I think these happen to be zoom decimal settings. Okay. Well, let's just go ahead and graph and see what we come up with. Cool. And it looks really similar to the graph Steve came up with. And in fact, this window we kind of left out. It just big enough vertically to include that turnaround point up here. If you try the trace, we actually have, it shows us the components of our function, though this is a long enough expression, we don't see all of it. But down here at the bottom, notice that we have 3 values, the t value, as well as the x and y coordinates. And so if I advance using a right arrow, it's incrementing. Notice the t is incrementing by 0.05. We saw that t step in there. And then we're seeing the coordinates of x and y as we're moving along the curve. Okay, so great. So that's a powerful tool. In terms of calculations, here's something I like to do when I've got a parametric function like this. I'm going to go back to y equals. And something that's nice and what's kind of cool is this will last when you change to other parametric situations. But in x2t, I'm going to go ahead and put for x2 and y2 the components of the velocity. So I'll go to the map menu. We're going to need a derivative. See that down at number 8, nderiv down here. Okay. That gives us this nice derivative template here. We're going to take the derivative with respect to t. Now your independent variable key here, the x comma t comma that changes depending on what mode you're in. Since we're in parametric mode, if I press that key, I'm going to get a t. Fantastic. And now I'm going to take the derivative of x1 of t. So when I get into my variables, I'll go to the y variables, go down to parametric. There's x1, put that in. And this may seem a little funny, but I'm going to actually put in t again here. So I'll say t equal t, because I want this to behave as a function. So I could actually literally graph the velocity vector function. Okay. They would take some interpretation of, because the points would be representing, the coordinates of the points would be representing the velocity components. But for calculation purposes, this is also very nice to have. Now I'm just going to follow suit quickly here. I'll just pull up nderiv again. I'm going to do the same thing for y2. I'm going to make it the derivative with respect to t of y1. Get in my y variable. Oops. Try that again. A little too fast. Y variables, let's go down to parametric. There we go. Put in y1. Oh, I am, my apologies. I got off on the wrong. Yeah, I'll just go ahead and put a t in there anyway. And I need to back up here, make sure I've entered that argument correctly. So let me get back into the variables. There we go. And I want y1. Okay, I think I finally got it there. So let me enter that. And just for grins, you know, we could go ahead and graph this. It's going to graph it. Now, interpretation-wise, you got to be really careful here. So each point on this, let me just go ahead and do a trace. So I'll go over. So at that point, -1, 0, if I switch over to the velocity function, these are the components of the velocity vector at this starting point over here. So this is telling me that the x component of the velocity is a positive 1.5, and the y component is close to positive 1. Now, if I think about that, what that's telling me is my point should be moving in the positive x direction and the positive y direction. And notice that on the curve, that's exactly what is happening. Okay, so I don't often do this graphing. The real reason I entered those was if I quit out of the graph, I now have a handy thing for calculating things that involve that velocity component. For example, Steve looked at the velocity at time t=1. So if I want to calculate that, I'll just bring up x2 of t and evaluate it at 1. Okay. And then similarly, I can do y2 of t and evaluate it at 1. Oh, you know what? I got the wrong y variable, didn't I? Okay, so let's delete that. And let's go back. And let me try that again. So parametric, I wanted y2 of t, because that's my real velocity component for y. There we go. So y2 of 1 okay.
Beautiful.
Now, supposedly these are the decimal versions of the x and y components of the velocity. Do we really believe it? I think Steve got the actual, using the cast, he got the symbolic ones. And if I remember right, let's see, I've got it written down here. His
I got 3 minus the square root of e over 2.
Okay. Actually, I'm going to check the y one first. I think Steve's y component of his velocity is negative pi over 2. Well, that's
right.
Looking pretty nice, pretty close. Negative 1.57. That's looking legitimate. Let's try 3 minus the square root of e.
Yep.
And let's see, it's just plain old e, right?
Right.
So I'll put a power 1 there. And then that's get out from underneath the square root sign and divided by 2. So this is the symbolic answer that Steve got. Let's look at a decimal equivalent of that approximation. Oh, nice. Look at that.
How about that?
Extremely close. Okay, so that numerical derivative is going to serve you well. Notice the other things you can do. You could calculate the speed by taking the square root of the sum of squares of the x2t and y2 of t. In fact, you can even do an acceleration, because I sometimes get this question, can you do a numerical derivative of a numerical derivative? Well, let's give it a shot and see what happens. I'm going to do n deriv again, derivative with respect to t. And I'm going to put now in, how about x2 of t? So now I'm taking the derivative of the velocity components.
Mm-hmm.
And let's see, we wanted to evaluate this at, was it t=1 again?
Yes, sir. Yep.
So just put 1 in. Enter that. Boom. And I think that was supposed to be negative square root of E again.
Mm-hmm.
I'll just put in e to the first, get out from under the square root sign, divide by 4. So that was Steve's symbolic answer for the x component of the acceleration. Let's see how close we did by taking in. Gotta like it. Yeah.
Pretty good.
So this works really well. You could, for example, if you integrate the speed function by taking the square root of the sum of the squares of the velocity components over an interval, do a numerical integral of that and get total distance traveled. It's just very, very powerful tool. Okay. Steve, if you're okay, could show off a little bit with the TI-Nspire too.
Sure.
Yeah. All right. So I'm going to switch platforms here, and that's what I'm going to need to. I'm going to do a quick stop share so that I can share a different platform here. Let's go over to the Nspire. And Steve mentioned the Monday night calculus sessions that he and I have been doing for, gosh, 2 or 3 years now. We're got a full slate this fall. They come up about every 2 weeks. I think our next one is actually this coming Monday. We usually concentrating on A/B topics. Occasionally we'll do a BC topic. Steve and I were recently working together, and we came up with some refreshing of some activities on TI in Focus AP Calculus. And one of the ones we did was the particle motion in the plane, perfectly appropriate for this this session here at TQ. So what I've done here is create a file on TI-Nspire that's really for teaching purposes. So I wanted to show you what this does. We're going to have the x of t, y of t are coordinates of our vector valued position function. And what we're going to do is I've set up a file here where you can put in a time interval, TBTF, that's for T beginning, T final. A time increment sounds a lot like the Windows settings for parametric. But then it's going to illustrate the velocity and acceleration vectors in the way Steve was describing, where you're actually attaching it to the point. Okay, so let's take a look at what this looks like. There we go. All right, this is moving a little bit slow here on me. Oh, maybe we won't do this. I don't know. Let's see. Okay. All right. So this is all right. It skipped ahead a couple of pages. That's just fine, in fact. So I haven't shown you what the equations for x and t, x and y are here. What you can see, I think, is the initial point looks like it's at 1, 2, 3, 4, 0. That's where my point is starting out. And I've got a slider up here that's going to increment the value of t. Now, without showing you the graph, I'm going to show you what the velocity vector and the acceleration vector are at this point. So this, and when t equals 0, here's my initial velocity vector. I think. There we go. And so just based on that, if I was to increment t, how do you think this particle is going to move? I won't put Marco on the spot. I'll put you on the spot, Steve.
Sure, it looks like it's going to move straight up, doesn't it?
Looks like straight up. Now, if this is a variable velocity, if it's a function that's not constant, I would actually expect as soon as I increment t, the velocity may start to change. what tells me how the velocity changes? Well, that's the acceleration vector. So now I'm going to show the acceleration vector. I hope. Let's see. There it is. Okay, so if this is moving straight up, do you think it's going to start bending to the left or the right?
Well, we think to the left, huh?
Yeah. And now if I increment t, with those things still shown, it's actually going to show me the new velocity and acceleration vector. So I would expect the velocity vector, let's see, the acceleration has, the y component of the acceleration is 0. So I would expect the y component of the velocity not to change much at all. But I would expect the x component of the velocity be in the negative x direction. So let's increment t. And we'll see what the next point is. There it is. Okay. And so now you can see, okay, and we keep incrementing t, it's showing me this moving particle with a velocity and acceleration vectors attached. Now, if you do want to see the path of the particle, down here at the in the graphics screen, it says show path or not. We can do that. And let's see the path. There we go. Okay, so there. So this is a tool I think that we created mainly for illustration and teaching purposes and being able to pose questions. So students really are thinking about what is it that the velocity and acceleration vector is telling them. Okay. Yep. So Steve, at this point, I think I'll want to stop sharing and turn it back over to you.
All righty. Thanks, Tom. Cool stuff. Very cool.
Very, very, very cool stuff. Gloria from South Texas loves the technology representation of these problems as well.
So this says example 4, Marco. There is an example 2 and an example 3, which we will post, but this example 4 is actually a homework problem. And maybe you could try this one with some of your best students. This is one of my favorite particle motion problems. Let me see if I can tell you why. There's some cool things in here. And there's some questions in which you can employ some of the technology tips that Tom just talked about. So here we have the motion of a particle. It's moving along a curve C, but notice what's given to us here. We're given a y of t, but we're given dx dt. Now, I've actually produced the curve for you here. But I think that's one of the very first things you might try to do. See if you can use your TI-84 or TI-Nspire to actually produce this graph for t between 0 and 10. That's a good question. What I'd like you to do on this one is to find the position of the particle at time t equal 4. Well, that's pretty straightforward, I guess. I can plug t equal 4 into the y function. But I wonder how I get that value of the x component, because I've got dx dt here. Well, I do know that at time t equal 2, the position is x equal 1. That might help a little bit. Find the acceleration vector. But be careful. This says when the speed is first equal to 1. That's a little twist on a problem here. A little bit different than just asking for the speed, or pardon me, the acceleration vector at a particular time. You've actually got to find this time first. This is a good example, I think, of this finding the intermediate value and storing that to the greatest degree of accuracy possible, and then bringing it back over and finding the acceleration. Find all the times t at which the tangent line to the curve is vertical. Well, I'm just going to do a little bit of scribbling. It looks like there might be a vertical tangent line over here, and then towards the left side of this curve, I'm not sure. It looks like there could be one in here. It looks like there might be one in there. So I wonder how you would go about finding that. We didn't really talk about that in the formula section, but how would you do that? Does the particle ever exceed a height of 2 or a y value of 2? So it looks like it gets really close up here. Is it ever above 2 or is it always below 2? And then finally, when you're all done with that, find the average speed of the particle between 0 and 10. So that's a good problem for your best PC students for tomorrow morning or Monday morning at 8 o'clock. And with the time that we have left, let's see if we can take a look at the scoring of one of these exams. Tom and I are frequently asked questions about how these problems are scored. We're still deeply involved in the scoring of the exam. And the information that's posted about the scoring guidelines has changed, I think, dramatically over the past 3 years, since actually the pandemic began. And there isn't, in my opinion, quite as much information posted. And so sometimes it's hard to discern what these scoring guidelines really mean. So we're going to take a quick look with the remaining time. We're going to take a look at the scoring of this problem. This is from 2022. This is on the BC exam. It was question 2, and this was a calculator active problem. And please, Marco, if you would be kind enough to watch the chat, if you have a question about how this was scored, please put that in the chat and we'll do our best to answer it. So here we have a particle moving along a curve in the XY plane. And this time we're given dx dt and dy dt. And we know that at 4, the position of the particle is 1, 5. So we know, although we don't have an expression for this, we do know that x of 4 is equal to 1. We know that y of 4 is equal to 5. I think that'll come into play here somewhere in this problem. Find the slope of the line tangent to the particle, tangent to the path of the particle at time t equal 4 was the first question, was part A. Well, that was worth only 1 point, and it was basically 1 point for the answer. 3 digits to the right of the decimal, rounded or truncated. Rounded or truncated, this was the exact same value, 0.701. What I did here, when I usually talk about the scoring of the exam, I like to show solutions, how I might do it a little bit more explicitly down below. And so that's what I've got down below here towards the bottom of my screen. If I can arrow up a little bit, there we go. We've got to find y prime of 4 over x prime of 4. And I actually started out by doing this symbolically. This is just a suggestion. If it's a calculator active problem, students don't have to present anything symbolically, except they should present the setup. And that just goes back to the general instructions on the exam. For any mathematical, for anything you go to your calculator for, you need to show the mathematical setup. And so we would want to see y prime of 4 over x prime of 4 is equal to 0.701 in order to earn that point. Symbolically, I think that's the answer, and that's not so bad. You can just plug a t equal 4 into both of those expressions that were given. And what the heck, well, I've got the TI-Nspire, there it is. I inputted or defined a function xp for x prime, yp for y prime, evaluated the quotient, there it is, and there's the decimal approximation. I feel pretty good about that. So 1 point for that. Oops, I'm sorry. 1 point for that, and in these new scoring guidelines, we're given scoring notes. Not that they're cryptic, but they're just not as detailed as what we used to get 5 or 10 years ago. So to earn this point, the student cannot just simply give you the 0.701. There must be some evidence of this setup. So we need to see this. That would be the best thing possible, I think. Or if they simply give us that symbolic expression, we're going to take that as enough evidence that they solved the problem in the correct way. Or this is probably right on that gray, right on that line. If they give us that symbolic answer, we believe they did it correctly. However, if a student simply responds with what I might call a bald answer, 0.701, they will not earn this point because we don't know where that came from. So this is common. This has occurred more frequently, and it actually occurs in several points in the scoring notes associated with this problem. This has occurred more frequently in the last, I'd say, 3 or 4 years, and I'm not sure exactly why. But students are equating functions with constant values. And so we saw a number of students who gave us the answer to this problem like this. Y prime of t over x prime of t is equal to that constant. Well, yes, this is the slope of the tangent line, but it's not equal to that function. And so this kind of a response does not earn the point. But this particular year, a student who did that was in some sense, I don't know what the right word is, vaccinated or inoculated, so that if they made the same sort of error later on, they would not be penalized again. So Tom and I are lucky enough to have access to what are called the question leader reports. And in these reports, we often gain information about how students performed on this question. And in this particular question, most students did recognize that's how you find the slope of the tangent line. However, there were some communication errors. You know that we're stressing good communication, good notation in AP Calculus. So we're looking for that when we score the exam. And unfortunately, some students return the reciprocal of the correct answer. Here's part B. Find the speed of the particle at time t equal 4 and find the acceleration vector of the particle at time t equal 4. This was actually worth 3 points. 1 point for the speed, there's the answer. And as you might expect, given what we've talked about already, we need some sort of indication about how the student got that problem, got that answer. And the acceleration vector, 1 point for one of the components, 1 point for the other component. So 3 total points here. Here's how I solve that one down below. There's the expression for the speed. We know that formula. We've got that one memorized. There it is symbolically. There's the numerical answer, 5.035, rounded or truncated. Here's the acceleration vector. Take the derivative of those two functions separately that were given to me. There's the symbolic answer. There's the numerical equivalent. And son of a gun, here it is with the TI-Nspire, which I think is really cool. I don't think I'd want to write down that symbolic answer on my AP Calculus exam. This is a calculator active question. There it is. There's the answer. And let's see, here's the acceleration vector. Very easy to get. There it is symbolically. Doesn't look quite like this. You can see that the TI-Nspire in some sense rationalized. There it is numerically. There's the symbolic component of the acceleration vector, the y component, and there it is numerically. Cool. So a few things about the scoring notes here. Well, to earn any of these points, we need to see the setup. This was worded a little oddly here. Let me see if I can sort of decipher all of this. To earn the first point, the student could simply write that. I find, I don't know if Tom will agree with me on this one, but I have found in recent years with calculator active questions, the responses can be very succinct. Interpret the problem, know what it's asking, write the mathematical expression, go to your calculator and get an answer and write it down. So if you write that, there's your first point. If we see this as an answer, this is equivalent to what we talked about in part A. We're going to accept that as evidence that the student conveyed enough, knew what they were doing. There's sort of a stop here. And if a student presents this, they'd earn both the second and the third point. That's enough evidence of the setup. So the bottom line here is that there must be some supporting work. We have a term when we score these problems, we sometimes talk about bald answers, and those are answers where we expect some sort of supporting work. The second and third points could, of course, be earned independently. If the acceleration vector is not presented in an order pair, the components must be labeled, right? So good communication skills are necessary. So for example, if we see one of these values on the screen, on the paper here, and another on the paper here, but they're not labeled, we can't assume that one of them is the X component and the other is the Y component. Good communication.
Say, Steve,
Yes, sir.
I think we're just about out of time, so I think we're
Okay.
gonna need to turn it back over to Marco here, so we can.
All right.
finish up.
Let me finish this.
Sorry,
let me
sorry to
finish-
interrupt you.
Let me finish this part and we'll turn it back over to him. If the two components of the acceleration vector are reversed, the student earns neither point. A response that correctly calculates, this is kind of weird, but we have sometimes special cases. If they give us those components symbolically, they can earn one of the 2 points. And this person here who reversed them, well, we'll give them one out of the 2 points also. And this is just a listing of some of the common errors. And you'll get this in the handout that we will send to Marco. All right, thanks, Tom. Thanks, Marco. I'm going to stop sharing. I'll turn it back over to you. Hope that was some good information for teachers.
It was. We had some really nice comments. Let me share the last few slides that we've got. Let's see. So just like I mentioned, we are going to select a winner of some technology in each one of our sessions. And just for full disclosure, transparency purposes, the way we selected the winner was by taking a double derivative of the total number of participants, looking at the acceleration vector and taking the sign of that, and adding 35, since 35 is the year that we've been holding this annual conference. And so the winner, if you're still with us, is Nancy Summer.
Oh, cool.
Nancy Summer, if you please send us your email address through the chat. I will document your email address, and someone from our conference will be in touch with the rest of the how we can get this technology out to you. Thank you all. Thank you, Steve. Thank you, Tom, for your time today. Thank you all. We hope that you enjoyed this session. And yes, hopefully, I think that we've got one more slot left for sessions. Hopefully, you guys will join us then. Thank you all very much.
Bye-bye.
Thanks, Tom.
Oh, thank you, Steve. Yeah, sorry that I interrupted you there at the
No,
end.
no, that's fine. I saw it, but I'm glad you did.
Okay.
Thank you.